Okay, hi everyone. So it's week 12. This week we'll be talking about reductions and intractability. Okay, it's quite the packed tutorial, so I hope to be able to cover some grounds first before we go through to some questions. Okay, so here's the table of contents. I'll spend some time doing the recap before we do the questions. It's quite unlikely that I'll finish everything. Question 4 in particular has some elements of greedy algorithm there. I think I won't talk about it. Let's see. Okay, but I'll try to cover as much as possible. Okay, so reductions. All right, so what's reduction about? And first of all, warning again, I feel anti-completeness is this topic that is most abstract in 3230. So try to pay attention, and if you are confused, do stop me. Okay, I'll try to pause a lot for questions. Okay, so quick recap, back for your discrete mathematics, CS1231 for most of us. So contrapositive, right? Recall that if P then Q, if there's a statement, if P then Q, the contrapositive is by negating Q. So it goes, if not Q, then not P. So this over here will go over here and you negate it. And this one over here will go there and you negate it as well. So that's contrapositive. Okay, there's the truth table here if you want to convince yourself that it's really the case. All right, but I won't spend too long on this slide. So another recap is that, again, if I have an integer x that's greater than or equals to 1, you need roughly like O log x bits to represent it in binary. Okay, so we'll need this fact a bit for today, but just keep in mind if you have a number x, you need roughly O log x bits to represent it. Okay, the exact number isn't that important for today. Just know it's big O of log x. Okay, so that's the recap. Now, so let's start talking about reductions, right? But before that, I'll talk about solving problems. So if you have given a certain problem A, like somebody just gives you an exam, you know, like, oh, I have this problem for you to solve. How do you go about solving it? Okay, so there are several ways, of course, if depending on the problem, of course, right? So first step, maybe one option is to give up because you don't know how to solve it. But jokes aside, right? You can try to come up with an algorithm for it normally. Like you're giving maybe something that's similar to a shortest path problem. So you might modify an existing shortest path algorithm and come up with algorithm for it normally, right? This is a possibility. Or you remember that you know how to solve some other problem, so you use that to help you. Okay, like for example, if as I said earlier, right, like you're given maybe a shortest path problem, you might think, oh, maybe Dijkstra can solve this problem, or maybe Bellman-Ford algorithm can also solve this problem. But maybe the problem was like the weights, instead of you add the weights, you multiply the weights. So can you make use of the problem in the past, solution in the past, like Dijkstra algorithm, in order to help you solve these problems? Okay, so essentially it's like somebody has done the hard work of solving some other problem, so why not just use it? Okay, so reductions, right, is set in this context where we try to think of the relationship between two problems. Okay, so the problem you have at hand and some other problem that has been solved before, or at least assuming it has a solution. Okay, so this reductions. So in terms of algorithm design, right, when you're trying to come up with the algorithm to solve problem A, you think of problem B that you already know how to solve. Okay, so you don't know how to solve A, but you know how to solve B. Okay, reduction is when you try to transform the type of input for A to the type of input for B. Okay, so the thing to take note here is that the problem B is black box, meaning that the solution, right, you should not modify. Okay, you're given the statement and you're given the solution. Let's just assume you already know how to solve it and you're given the solution in a black box in terms of like input and output. Okay, so you must not modify it. And this might be something that you are not used to, or at least when I was a student, this was something that I wasn't very used to. But what is allowed, right, is not for you to modify the solution, but rather for you to modify the input. Okay, so you get the input for A, right? And then you prepare an input for B based on the input for A by making some modifications. Okay, so you just tweak your input, but let the algorithm, the solution, handle the rest. Okay, so the pseudocode roughly looks like this. If you're trying to solve the problem A and it's the input A, right, the type of the input, it can be anything, right? It can, maybe it's a number, maybe it's a boolean, maybe it's a string, right? So you get certain kind of input for A. And then what you do is by doing a reduction from A to B, it means that you transform the type. Okay, you do some manipulation based on the input to A and you get the input to B. Okay, and then you use the solution to B that is magically given. It's black box. You must not modify this solution in order to get the output for B. Okay, but because remember, at the end of the day, our goal is to output the correct answer for the problem A. So we need to do some transformation in the other direction. Okay, so transform the output to B, output of B to output of A, and then you return it. So at a high level, this is really what reductions is all about. It's really like you transform the input to a suitable type that is suitable for use for the problem B. Okay, then use that magically known solution to get some output, and then convert the output to some format that you want it to be. Okay, and this is actually the diagram that if you have seen the lecture, this is the exact diagram that Prof used, right? And this is essentially what in pseudocode, this diagram is trying to give a pictorial view of this pseudocode. Okay, so right. So here's a toy example, right? For me, just to give you an idea of what I'm trying to say. So problem A is, let's say you want interested to find the minimum of element in an array, right? Problem B, something that you already know how to solve, is finding the maximum element in an array. Okay, so very similar problems. Of course, you can always come up with an algorithm for A yourself, but the goal here today is to make use of problem B to solve problem A. So the reduction is by negating all the elements in the array. Okay, and the intuition here is that, you know, if you want the minimum element in the array, if you negate everything, this minimum will become the maximum in problem B. Okay, so here's how the pseudocode will kind of look like, right? So you get the input for A, which is an array, right? To find the minimum in an array, you get an array. The reduction is the transformation by multiplying everything by -1. Okay, by negating everything. Okay, by negating everything. And then you use the maximum in array, which you already know how to solve. Okay, you magically already know how to solve it to get the output for B. Okay, and then you transform back the result to the format that you want by again negating the answer to get output of A. So for example, input A here is this -3, -1025. What you want to output is this thing. Okay, so the reduction is by negating every element. Okay, and then the output is because you output the maximum of input B, it outputs 3, so you get 3, right? But what we want is -3, so the output to A is actually -3 by negating it. Okay, so this is like a very toy example just to give an illustration of reduction in the design perspective. Okay, so we haven't touched more on like the analysis part. I'm gonna talk about it soon, but any questions about this part? Okay, I'm gonna pause here for a quick question. Any? Hope it's simple enough for now. This is something that you all should be familiar about from your like 2040 or like data structures and algorithms, where you use different problems to solve new problems. Okay, so just type it in the chat in case you have, but I'll go on. Okay, so now we'll talk about the analysis perspective, and this is something new, maybe something you haven't seen before. It's only in 3230 that maybe you have just seen it. Okay, so for the purpose of these chapters, we use reductions to consider the hardness between problems. So hardness, you can think of it as the class of the time for the problem. If we say something is easily solvable, means that we have a polynomial time algorithm. And polynomial time here means that it's O(n) power some constant. So for example, n power 2, n power 100, n power 1 million, these are all polynomial time algorithms. Okay. Hard, when we say something is hard, typically we say that it has an exponential time algorithm. Okay, so something like O2 power n, that's bad, right? This is a hard problem, typically. Okay, so we'll show that if problem A has a polynomial time reduction to problem B, then B is at least as hard as A. Okay, it's okay if you don't understand this statement yet. We'll try to see it very soon. Okay, so one thing to take note, and I think Prof discussed this in lecture, is that we usually discuss polynomial time with respect to the encoding of the input. What does this mean? Okay, so if an input is a number n, the encoding is O log n bits. Okay, like the way the computer sees a number n is that it sees, oh, there are log n bits. Okay, so an array of n elements with maximum value capital M, right, is O(n) log m bits. Okay, why? Because let's say you have n elements, right? There are n of them, little n of them. Each one of them is upper bounded by capital M. And each of these capital M is O log M. O log M, O log M, O log M, right? So multiplying each of the log M bits by n, we have the representation, the encoding of input with O(n) log M bits. Okay, so why we care about this encoding of input actually has to do with theory of computation related to things like Turing machine and so on, but you don't need to know the Turing machine part. You just need to know that when we discuss polynomial time, it's with respect to encoding of input. Okay, so for example, let's say I have this algorithm, right? The algorithm takes in n, a number n as input, and then loops n times. Okay, so well, if you go to your like CS1010 or CS2040 kind of like definition, you know that this is an algorithm that runs it O(n) time, right? But in 3230, sure, this is still O(n) time, but we let's analyze. Okay, so let ENC be denote the input encoding. So ENC is O log n, right? The encoding of the input is log n bits. Okay, but the time here, as I said earlier, is O(n), right? Is O(n), and this is O of 2 power log n. Why? Because well, there's this property that 2 log 2n is this is by logarithm rules. Okay, by logarithm rules, this is equal. Okay, so this is O2 power log n. So means that this is something like O of 2 power the encoding. Okay, something like 2 power the encoding. So with respect to the encoding of the input, this algorithm is actually exponential time. Okay, so you see that this is O(n). Now this is where I think like some people might need to shift their thinking a bit. Okay, so although this is O(n) time, right? So it's kind of like linear with respect to the numeric value of n. Okay, but with respect to the encoding of n, it is exponential. Okay, so I'll say that again. This algorithm, indeed, it is O(n), means that it's polynomial or linear with respect to the numeric value of n. But with respect to the encoding of the input, think of it as like how many bits is required, how many bits of input are given. It is actually exponential time. Okay, so it's just a minor technicality to take note. Okay, so in example 2, right, here I'm given an array. So slight difference here. You're given an array nums, right? The array size is n. Okay, and the max value, let's say, is n. Okay, let's say the max value is also n. So the encoding is O(n) log n, because every of the value is like at most n, at most n, at most n, and the size is n. Okay, so again, this algorithm also runs in O(n) time. Like nothing special, it's just loop through the array. But because we change the input encoding, right? So instead of giving a numeric value, we give it an array of size n, right? Give it an array of size n, there are n values, and the encoding is O(n) log n. With respect to the encoding, this time is actually polynomial time, right? It's no longer exponential. Okay, so it's a bit tricky here, but I just want you to take note that the input encoding is really what we are basing it when we discuss like, oh, what is polynomial time, what is exponential time? We do it with respect to the encoding of input. Okay, so I hope just take this in mind, but there's no need to like stress over it. But again, like whenever you are saying something is polynomial time, just keep this in mind. If you have any questions, feel free to put it in the chat, but I'm just gonna keep going on for now. Okay, so again, this is the pseudocode we saw just now. So we say that this is a polynomial time reduction. Pn time reduction is polynomial time reduction. If you know this reduction and this transformation takes polynomial time. Okay, and let's analyze like the total runtime of this entire solver. Okay, so assume, right, solving B, the solve B takes Tn time. Okay, takes Tn time, and because you have input B, right? Input B that has Pn time, it has I think I'm confusing myself. Okay, so the reduction the reduction takes polynomial time. Okay, so input B must be at most Pn. The space complexity, like kind of like the space complexity of the input B should be at most Pn, polynomial as well, because it takes that much time to read input from A as well. Okay. Okay, so input B must be of size at most this much because the reduction takes that much time. Sorry, okay, so there's a question, a private question. Can you explain again why the encoding changed between the slides? Okay, sure. So example 1 and example 2 are completely different problems, okay, or completely different algorithms. Okay, the algorithm 1, what it does is it takes just a numeric value and makes use of the numeric value n. Okay, I tell you, hey, can you loop 5 times, maybe for example. Okay, can you loop 5 times? Okay, then the second algorithm takes as input not the number 5, but rather it takes in an array of 5 values. Okay, takes an array of 5 values. Let's say all of them like 5, 1, 3, 5, 2. So it takes in an array of 5 values. So the reason why the encoding changed between the different slides is really because the input to the 2 different problems are different. One takes in a number, one takes in an array of numbers. Okay, so intuitively, like if I give you an array of numbers, it takes up more space, right? You need more things to encode an array of numbers rather than giving you like a single number. So that's why the encoding changed, because here the encoding is like O log n, and here the encoding is On log n, because the numeric value is n, but I give you n of such things. Does that answer the question? Yep, no problem. Okay, so let me go on. Okay, so as I was saying here, the reduction takes in polynomial time. So the size of the input, right, it's also polynomial size. Okay, so because of that, this output B, right, is T of Pn, because the size of input B, this is size of B, is at most something like size of input B is at most polynomial time. So it takes Tpn time for the step output B. Okay, so in total, the time to do this algorithm solving A, right, it takes Tpn time. Okay, this is the time for step 2. So this is step 2, line 2, and this is like step 1 and 4, or line 1 and 4. Okay, so this is the total time to solve A, assuming you're making use of an algorithm for B. Okay, that you know that you can solve in Tn time. But this is where we make use of the relationship of the hardness of the different problems. Okay, so why? Because this is the time to solve B, right? This is the time for step 2. Okay, if the polynomial time is possible, meaning this entire thing runs its On time, On power C, sorry, right? Then you add some more polynomial time, n power d, like let's differentiate the constant, like it's On power d for this one. So this entire thing will also become polynomial time, like let's say On power e, whatever, like what the constant is doesn't really matter. But again, I'm trying to say that if step number 2, right, it's possible that this runs in polynomial time, Tpn is something polynomial time. If you add them up, if you add up to the other one, right? If you add up to the other remaining steps, which is also running in polynomial time, the entire thing is polynomial time. So it means that whenever you have a problem B that you can solve in polynomial time, you get the solution of problem A also in polynomial time for free. Okay? So, all right. So if that's confusing, ask me to repeat, but I'm going to go to the next slide. So this is notation for reduction from A to B. Reduction from A to B. Again, this is what I said in the previous slide. If B has a polynomial time algorithm, A also has a polynomial time algorithm, because you make use of problem B in order to solve problem A. Okay? So a way to interpret the previous statement is that if B is easily solvable, then A is also easily solvable. Okay? And the contrapositive of this statement is If A is hard, so you negate A. If the problem A is hard, then B is also hard. And that's why this last statement is kind of like the reason why the notation is like that, right? So there's the less than equals to, like greater than equals to, whichever, there's this inequality looking symbol, right? And this is in terms of hardness. So you can think of it like, oh, B is greater than A in terms of hardness. So like this is the hardness. B is harder than A. Okay. So B is at least as hard as A. That's the terminology I'll say, right? So here's the intuition in case that's still confusing, right? So let's say, right, these boxes are algorithms to solve A. Okay. And well, the algorithm to solve A, they usually have like different kind of complexities to do it, right? Using B might not be the best way. So B is just one way you can solve problem A. You can solve problem A via like any way you want. Okay, using B is just one way. So we want to show if A is hard, then B is at least as hard as A. Suppose not, right? Suppose B is actually easy, right? Suppose we have a polytime solution for B. So it's this box over here. Right? This is the solution for B. It takes up like faster than polynomial time. So because the algorithm for A depends on the algorithm for B, it must mean that the algorithm for A, right, it must also be polynomial time because it depends on the algorithm for B. It makes use of algorithm for B to solve the problem for A. Okay, so it means that this problem A must also be easy, because this is a polynomial time solution for A. Okay, and this is a contradiction because initially we assume B is actually easy, right? We want to prove this statement. We assume not, by contradiction, B is actually something that's easy, but then it directly contradicts this A is hard statement and therefore completing the proof. Okay, so the intuition here to keep is that whenever we can solve B efficiently, right? Whenever you can solve the problem B efficiently, we also get an efficient algorithm for A for free, like double quote for free, because we use B as a subroutine. Okay, so this is one direction, right? But the other direction doesn't hold. So if I say that A is easy, right? Just now I say A is hard, that means B is hard. But if A is easy, it does not say anything about B. Why? Because intuition-wise, how I see it is that A could have been easy because of another algorithm. Again, as I said, the problem B is just one way. It's just one way you can solve A. There are many other ways that might be more efficient. Okay, for example, like this box over here, doing something. I don't know what it's doing, but basically it's something that's polynomial time, thus making the entire problem A something that's easy. Okay, so A could have been easy because of another algorithm. So it really doesn't say anything about the quantum complexity of B. A simple example, I hope, is like, so problem, find minimum, right? Find minimum. So there is an ON solution, ON time solution by linear search. But there is a way to do like sort first, right? Sort takes ON log N and access first element and take first element. Like there are two algorithms, right? The fact that, you know, like let's say ON here is easy and ON log N is something like hard, right? So if ON here, because finding minimum, just because it has an ON time solution, it doesn't say anything about the sorting problem. It doesn't say that sorting problem is also easy. Okay, so like here's just a concrete example as to why, like, if A is easy, it does not say anything about B. Because let's say the problem of finding minimum is ON time, right? You can there's an algorithm that runs at ON time to solve the finding minimum by doing a linear search. But it doesn't say anything about the other problem, which is sorting, that we have a reduction to. Okay, so this is why this does not hold. So keep this in mind, and it's important again. So this is arguably the most important slide I feel for the entire like study of NP completeness, is that there's this relationship. If you can reduce from A to B, it means that if A is hard, then B is at least as hard as A. Okay, and I want you to take note, right? It's very important. Please get the direction of the reduction right. Okay, so don't confuse where you start from. Always start from to show that a particular problem is hard, right? So for example, I want to show that B is hard. Okay, you need to reduce from a hard problem A. Okay, so start from something that's hard, start from A that is hard, then do a reduction from A to B, to show that B is also hard. Okay, so this will make more sense maybe like in the next lecture, but I just want to highlight it now that the direction of the reduction is important. Okay, so if you get it wrong in the exam and you get the direction wrong, you are proving an entirely different thing. So it's quite likely you might even get 0 marks for that question. Like the entire question you've gone just because you started from the wrong direction. Okay, just because you're proving the wrong thing. And if I'm a grader and you are one of my students and I see you doing the wrong direction, I might give you negative marks. Okay, no, I'm just kidding. I'm not a grader, but that's just how important the direction is. Okay, so any questions about this? But yeah, I have a few more slides before like we even begin the questions. Okay, so again, PM me or put in the chat if you have further questions. But again, I'll go on with the decision problems. So decision problems is this, the essence of decision problem is it just takes in an input and then it outputs yes or no. Can think of it as like problems that the output is a Boolean value. Okay, a terminology is that a yes instance is the input to the problem that will output yes or true, right? No instance is the input to the problem that will output no. So we call the pseudocode just now. We can simplify things a lot. We can omit the last step of transforming from output B to output A. Because what we do is that we take in the input to A, right? We expect the entire algorithm to return a Boolean. When we do the reduction, we transform from the input type A to input type B. Okay, and then we use the magical solver that we are given. But because both A and B are decision problems, the solver for B will output a Boolean value. So because, well, the output type matches, you can just output it without any problem, without needing to convert it from one to another. Okay, so this is the output to B. So this is also, the next part is also quite important. When is this algorithm like correct? Okay, so first of all, it's correct if input A is a yes instance, then input B is also a yes instance. This means that if problem A should expect to return true, you should expect that the solver for B also outputs true. Okay, this is what we want. We want it to be consistent, right? Both if A returns true, then B should also return true because we're just outputting it like that. Okay, the other way also holds. If input A is a no instance, meaning that you expect it to return false, then input B that you transform, right? After you do a transformation, it should also give you a input that returns false for the problem B. Okay, and also this means that this reduction must do the right thing and cleverly transform. And this is what you have to prove. You prove that the transformation from A to B is correct, is doing the right thing. You have to prove that the transformation is correct. Okay, typically, in terms of proving, we do the contrapositive for the second statement. So just now was A is no means that B is no. Typically, this is harder. To prove. So what we do is we take the contrapositive by showing that input B is a yes instance, implies that input A is a yes instance. So this, if you have seen the lecture, this might be familiar. Okay. So again, we want a polynomial time reduction. So polynomial time reduction just means that the transformation takes polynomial time in the size of the input A with respect to the encoding of A. Okay. So coming up with a reduction, with a proper reduction, will involve you to prepare input B, come up with a scheme, like how will you transform from A to B, okay? And then you prove that this transformation satisfies this property, 3 properties above, okay? So any questions? This is the end of the recap. If you have any questions, please let me know now, okay? Like if you're okay, please give me a thumbs up. If not, I'll wait for like a minute, because that's just how important the recap is, I feel. Okay. Just a couple of thumbs up. Okay, the rest, is it just like not a bit lost, or like you didn't listen in the first place. If there's any part you want me to repeat, let me know now. Okay. Okay. So, excuse me. Excuse me for the verb. Okay. So, okay, the first question is reducibility between optimization and decision problems. Okay. So, as I said in the Telegram group chat, we will see a lot of problems today just for the purpose of the questions. The first question is this problem called graph coloring. Given a graph, we color the vertex with a set of colors. Okay, or give it an ID if you like. Okay, such that the colors of, if they are neighbors, right? If they are neighbors, we want the color to be different. So for example, here this is blue, and this one is red. So they are different colors if there's an edge between them. But if, for example, I have two nodes, right, and both of them are like blue and blue, this is not a legal coloring. So this is a graph coloring problem. Okay, there are two kinds of ways to frame this problem. There is the optimization version, which is the minimum number of colors to color the graph. Okay, it's very trivial. If you have n nodes, you just color everything differently. That's trivial. It's a valid coloring if you color every single node differently, right? But the challenge, the optimization challenge, is the minimum number of colors required to color the graph. Okay, the decision problem is asking, hey, can you color this graph with k or fewer colors? Okay, so there is this whole string of like long paragraph of question. Okay, but have a read. Okay, this is basically asking if you can solve one, can you solve the other? Okay, and that's the entire option basically. If you have optimization problem solution, can you solve the decision problem version? Okay, so I'll give you some time to like read, and again, I'll give opportunities to ask questions. All right, so pick which one you think is true. Okay, the option is too long, so I didn't put it in the tutorial sheet. Okay. So let's resume at 11:36. Maybe 35. Okay, it's 11:35. I'll resume in the interest of time. So I've taken a look at the archipelago. I think it's quite expected, this distribution. But I want to mention one thing. So minimally, I hope it's you can recognize that 1 and 3, right? And 2 and 4, they are contrapositives of each other. So meaning that if one is true, that means 3 is also true because they are contrapositives of each other. 1 and 3 are saying the exact same thing because they are contrapositives of each other. So the answer should minimally come in pairs. Okay, it's okay if you didn't recognize it, but just if you look carefully, they are actually contrapositive of each other. So that's one thing. Okay, and a lot of you chose the 1 and 3 pair. Okay, and I think that's expected. The surprising one is 2 and 4 is actually correct also. Okay, let's see why. So option 1 says that, hey, if you can solve optimization problem, can you solve the decision problem? Okay, so this is very easy to verify, right? Because what you do is that the reduction is like this. Just use that optimization solution, right? Sorry. So if you get the input, if you have an input, what you do is you just do nothing to the input, use the optimization solution to obtain the value X, which let's say is the minimum number of the colors, right? Which is the minimum number of colors. Then what you do to solve the decision problem to return true or false is by checking if, hey, is this number X, the best that we can do is X, is the number that we can do best is less than equals to K or not, right? Because if it's possible to color with less than K colors, okay, if the best answer can be colored with K or few colors, then we have if possible, to color it with less than K colors. So I want you to quickly pause and think, this is reduction from what to what? Is it from optimization to decision or from decision to optimization? Okay, so give it like a 10-second thought, PM me if you know, if not, then it's fine. Okay. Okay, decision to optimization, let's see. Okay, so this is indeed a reduction from decision problem to optimization, because what we want to do is to solve the decision problem. Okay, and we make use of the optimization problem as the routine. Okay, so this is reduction from decision to optimization. So similarly, option 2 is the other way around. We are trying to see whether there is a reduction from optimization to decision problems. And this is a bit funky. The first time I saw this, I was like, oh, wow, that's possible. Okay, so interestingly, what you do, right, is that you just linear search on the value K. Okay, what this means is that you start, right, asking the decision problem, hey, can you solve the problem with one color? If not, then you search, hey, can it be solved with two colors? If not, then hey, can you solve it with the 3 colors? And then you go on until the first value that hits that says decision problem will say, yes, I can solve it with like 5 colors, for example. And that is the minimum value required for the optimization problem. So again, here's what I just said. Check if 1 is the minimum. If not, check if 2 minimum until the very end. Okay. And the tricky part here is that the reduction needs to be done in polynomial time. You don't have to do it like you don't have to care about the power of the polynomial, right? It can be n squared, it can be n cubed, but we have a polynomial time solution for decision problem. Okay, and the reduction is done in polynomial time because you're just going to check at most the number of nodes. It's polynomial in the size of input. Okay, so the entire thing still takes polynomial time. So you're just doing the checks polynomial time. Okay, you're just doing the checks multiple times, right? Just doing checks multiple times, and it still takes polynomial time. Okay, so this is why this is the reduction, and that's why you can solve the decision by being able to solve the decision problem. You can solve the optimization problem also in polynomial time. Okay. All right. So is this confusing? I'll just pause here in case this is confusing. The essential idea of this slide is that you don't know which one that is the minimum, so check every single one of them. But checking every single one of them is still polynomial time. Okay, so it's also possible, and that's why we just study decision problems, because they are both decision problems and optimization problems. They are in a sense equivalent. You can reduce from one to the other, and reduce from the other to the self in polynomial time. Okay, option 3 and option 4, again, as I said earlier, they are just contrapositives, so I won't talk much about it. Okay, they're equivalent. If 1 and 2 are true, then 3 and 4 are also true. All right, so I'll go on to the next question. The next question introduces 2 new problems. The partition problem is given a set of positive integers S. Can the set be partitioned into 2 sets? Can you partition into 2 things of equal total sum? So let's say this is the set of input, right? You want to check, can it be partitioned into 2 such that the total sum is equal? So here, the total sum, it is possible because the total sum here is 32 and this is 32. So they can be partitioned into 2, right? A simple example that cannot be partitioned is 1 and 3, right? No matter, because you cannot split the number apart, right? No matter how you separate the partition, it's going to end up like either 1, 3, or it's going to end up like 1, 3 and empty, right? Which is both are not, basically this is not partitionable, okay? The ball partition problem is given k balls, can we divide the balls into 2 boxes with an equal number of balls? So let's say I have like 4 balls, right? Well, very simply, separate to 2 boxes. They are both equal. They are 2 and 2, right? So this is the ball partition problem. If I have k balls, can you divide these k balls so that you have 2 boxes with equal number of balls? And I hope this is clear that it's a yes means that it's possible if and only if the k is even, right? Because if k is odd, if I have 5 balls, for example, there's no way you can split the ball such that one has equal to the other. Okay. So these are the 2 problems. Okay. So the question is proposing this reduction. Okay. It tries to say that, hey, I want to solve the problem partition, right? Solve the partition problem. I want to do it by attempting a reduction to ball partition. And this is what I do. The input to the partition problem is a single array, right? It's a single array of n numbers, of how many numbers, right? Set or array, whatever, right? The input to the ball partition problem is not an array, but rather it's an integer, right? It's an integer, a single number. So the reduction that this tutorial proposes is that, let me do a reduction by summing up everything. By summing up everything, and then I get a single integer, and I put it as input to the ball partition problem. Okay, then the idea is that I rely on the ball partition problem to tell me whether it's possible or not after I do the reduction. Okay, is this reduction clear? Is it clear what they are trying to do? Okay, so I'll give you some time to think about it. So is there something wrong with this transformation, or is there nothing wrong? Okay, so this AS thingy is that if there is a yes solution to the wait, let me think. Problem. So okay, so this slide is trying to say if I have a yes solution to AS is after the transformation, right? After the transformation, if I have yes solution to the ball partition, it does not imply a yes solution to the original problem. Okay, so this is ball. This is the partition. This is partition. This is ball. So again, recall the criteria for the reduction to be correct is that yes for one implies the yes for the other, and vice versa. And then the transformation runs in polynomial time. So think about it like I think no need to fill in archipelago, but if you have fill in, do it's fine. Okay. But what's a potential problem with this reduction? And if the reduction is correct, what does it mean for partition to ball reduce to ball partition? Which one is harder? Okay, I want you to like think of this stuff. Okay, I'll resume in a minute. Just give you some time to read the problem and ask me questions if you have any. Okay. Okay, I'll resume. Okay, so there is actually a problem with the transformation, and option 2 is the choice to choose. Okay, why? So it's trying to say that okay, yeah. So okay, so if AS is a ball partition problem and S is a partition problem, let's say, right, our initial input is 1 and 3, right? Initial input is 1 and 3 as I gave just now. The total sum, the reduction is because I add up everything. I add up everything, the answer is 4. And then the ball partition problem will tell you, oh, you have 4 balls? Okay, I can partition it, right? But it says that it can be partitioned when in fact the original input, 1 and 3, cannot be partitioned. So this is why the reduction is not correct, because for a particular input, let's say 1 and 3 like this, if you do the reduction, the ball partition problem will say that, oh, it can be ball partitioned, but in fact, the original problem cannot be partitioned. Okay, so option 3 is actually correct. It's fine. Why? Because it means that if the answer to partition is yes, then let the sum of the single partition be x, right? So we assume that this input S can be partitioned. It means that it's possible to do this. Now there are two partitions, X and let's say both the sizes are equal, right? X and X. That's the definition of a partition. The total sum is 2x, right? Because X plus X is 2x. Total sum is 2x. Then we consult, hey, ball partition, can you ball partition 2x? Okay, but because 2x is an even number, right? 2 times anything is an even number. It means that the ball partition will always return yes. Okay, so if we start off with a problem for partition that is yes instance, forget about all the no instances. Just care about the yes instances. We get the total sum to be an even number, and the ball partition will return yes. Okay, so option 4 is fine because we just add things, adding things up just run in polynomial time in total. Okay, so I'll skip this part, but I want you to think like, if say it was correct, what is the relationship between the two? All right. So I'll go to the question 3. It's slightly more involved, but ask me if you have any questions. Okay. So partition, again, I start with the partition problem. Okay. Then there's a knapsack problem, which if you watch the dynamic programming lecture, you might be familiar with, but I'll describe it again. So I have n items. So here I have 5 items here. It's a pair. It has some weight and it has value. Okay, so I have a knapsack and I want to choose a subset of items such that it's not too heavy. The bag is not too heavy after I put all these items, but I want to like gain some value out of the items, right? I don't want to keep choosing the cheap items. I want, even if the bag I max out the capacity, I at least gain some value. Okay, so for example, let's say I want the W to be 15. I want the bag to contain at most 15 kg, but it has $14 at least. Okay, and well, if I have these 3 items, this problem is a yes instance to 15 and 14. Sorry, with this set of items, and W equals 15 and B equals to 14 is a yes instance because the total weight is 7. 1 plus 4 plus 2, that's 7. And the total value of these items is at least 40. 2 plus 10 plus 2. I think I made a typo here. This should be 2. Okay, so it's at least 14. Okay, so it satisfies. There is a subset of items that is at least this much in value, but at most in 15 kg. So the reduction that they propose is interesting. Okay, so given the input to partition, they look like very different problems. Okay, given the input to partition. Okay, so what you do is just you pair them up. You make the value to partition become like the pair of the weight and the value. Okay, 18, 18, 2, 2, 8, 8, 5, 5, 7, 7. And then you're interested to find like, hey, is it possible to have the weight less than equals to 32? And 32 comes from summing everything up, summing the entire partition, summing the entire input to partition, and then dividing by 2. So you get 64 divided by 2, and then set it to this value. Okay. So again, I want to emphasize the input to partition is a single array. The input to knapsack is like an array of pairs, an array of n pairs, and the value W and value V. The reduction, the transformation is by setting these specific values. I consult the knapsack problem by constructing an input such that the pairs are actually the same, right? They come from the partition and they are the same. The weight itself, the value W and V are exactly S over 2 and S over 2. Okay, so the question is this reduction correct? And this problem, like, do pay attention because I think one of the assignment questions uses mentions this problem. Okay, so again, no need to fill in archipelago because we are running out of time. But is this correct? Right? So do think about it. Okay, so I hope you have had enough time to at least like understand what the reduction is doing. Okay, so actually all of them are correct. It's a correct reduction. Okay, why? So let's prove the first statement, right? So if I have a yes instance to partition, does that mean that after the reduction, it stays as a yes instance to the knapsack problem? So the reason is because if I have the yes answer to partition, it means that I can partition it, right, into two sets with equal sum, right? Then I simply use that same subset of items to be the subset of items that satisfies the knapsack problem. Because here, right, I know for sure 8 and 24, they sum up to 32, which is like half of the entire thing, right? So use this, the existence of these pair of items, 8, and 24, 24, it means that the weight itself, if you add up, it is less than equals to 32. In fact, it's exactly equals to 32. The value threshold, right, is also at least 32 because it is exactly 32 as well. So that's why in the one direction, if you have a yes instance to partition, it's also a yes instance to knapsack after the reduction. Okay. So this is the first option. The second option, right? So this is a bit trickier to argue. If I have a yes instance to knapsack, it means that we have a subset with total weight less than equals to S over 2 and total value at least S over 2, because this is what it means to solve the knapsack problem. Okay, to solve the knapsack problem, means that we have this subset such that the total weight is less than S over 2 and the total value is greater than equals to S over 2. Okay, so let's say, right, S over 2 is again 32. The question I'm interested to ask is that, is it possible, right, that weight equals to 30 and total value is less than equals to 30, greater than 35, for example, like specific value, right? Because we say that it's less than equals to and greater than equals to. So if this is 32, right? Weight can all be, and this is value, can all be lying in this range, and weight can all be lying in this range. The answer must have weight weight less than equals to 32 and value greater than equals to 32. So it can, theoretically, it can lie within any of this range. But what we want to argue that it's actually going to end up exactly at this position. The only answer possible is going to lie in this exact value 32. That's what we want to argue. Okay, so it's not possible because in the transform instance, the weight equals to the value. Like the way we design the input is such that the weight equals to the value. So it must be the case that total weight equals to the total value. And the only way it's possible is that it's exactly at the midpoint mark here, exactly equals to 32, exactly equals to S over 2. Okay, so it is not possible. So if the input to knapsack is going to have like weight and value that are different, they must be exactly equal. Okay, and the only possible value is S over 2. Okay, so the same thing, now we know that, all these value must be exactly equal. So use the resulting subset for partition as well, right? X1 and X2. So we argue that these two must sum up to like exactly half by the design of the input to knapsack. Okay, so using the result subset for partition as well. So I think this might be confusing, but so transformation, I'll just finish first, I'll conclude first. Okay, so transformation, again, it runs in polynomial time because it simply copies the weight and the value and adds them up, right? So we satisfy the criteria for the polynomial time reduction. Yeah, sure. Yeah, please, if you need to leave, just leave. Okay, I'll try to, it's recorded, so hopefully I get to finish some parts. Okay, so sorry about not finishing everything. Yeah, so partition to knapsack, we have a reduction from partition to knapsack. Okay, and this means that knapsack is at least as hard as the knapsack is at least as hard as the partition problem. So if there's a polynomial time solution for knapsack, there's also a polynomial time solution for partition. Okay, so because we ran out of time, I will at least like conclude the slides, right? So to summarize what we learned today is that we learn about reduction and how they can be used to compare hardness of different problems. Okay, so to summarize, this is arguably the most important slide, I feel. is the relationship. If you know a reduction from A to B, right, it means that all these statements are true. Okay, A is hard, then so is B. And I want you to remember, please get the direction of the reduction right. Okay, so I'll share the slides and I'll open for like questions for now. But if not, then I will resume with a bit of question 4 maybe. So I'll talk a bit of question 4 because it's recorded anyway. So I'll share the slides in the Zoom chat. If you have any questions, you can ask me first. If not, I'll resume with covering question 4. So yeah, sorry for not completing. I fully expected this because it's just a loaded tutorial. I'll pause for questions, but if not, I'll resume with a bit of question 4. For question 2, yep, okay. Second choice, yep. Mm-hmm. Okay. So okay, so you're in the right direction there. You say, is it because the case where the number of balls is 2? It's almost. It's because, as you said, right? It's not because the number of balls is 2, but it's because the number of balls is 4. Okay, so the reduction, right? The number 2, I presume you sum up the number of elements in the set. So it's not the number of elements in the set, but rather it is the total value of the partition. So the reduction is summing up the elements. It's not counting how many elements there are. So if I start off with a 1, 3 in the set, I sum up the value, it becomes 4. 1 plus 3 is 4, right? And as you say, in this case, right, if there are 4, if the input to the ball partition is 4, then it becomes a yes instance for the ball partition problem. But the original input to the partition problem, where the number 4 came from, cannot be partitioned. Does this clarify? Okay, great. Okay, so I'll resume with the problem 4. All right. I'll only cover A and E because I think that's the more interesting part. Okay. So, all right. So again, this is recorded. If you have to leave, please, that's okay. All right. So question 4. So I changed the title a bit to McDonald's instead of Yuck-donald's because I think Yuck-donald's is a bit mean. But McDonald's, let's say, so you're in Orchard Road. They want to open as many chain restaurants as possible, right? You have found suitable locations. Like let's say there are 13 locations here, A1 to A13, okay, that you want to place the restaurant. But the thing is, right, when you place them, you want them to be at least D distance apart to minimize competition. Because, you know, if they are neighbors, then maybe business isn't so good. So there's this criteria that every position that you want to put has to be at least equals to D in terms of distance, okay? So this is the first problem, right, that's introduced. You want to find positions in the restaurant such that the 2 adjacent positions must be at least equals to D. Okay, so the other problem is the independent set, and I think this is covered in one of the assignments recently, so I won't spend too long. Independent set is really finding a subset of vertices such that no 2 vertices in the graph is connected by an edge. Okay, so here, for example, this is not an independent set because if the 2 blue nodes they have an edge in the original graph, that means they are not part of the independent set. The problem of maximum independent set is to find the largest subset of V, okay? Because it's very trivial for you to just return nothing, and that's trivially an independent set because there's no even node to talk in the first place. But the maximum independent set is the largest subset of V, okay? So here, right, 4A is basically asking for a reduction. Can you model this placement problem as a maximum independent set problem. Okay, meaning, right, this is to design an input graph starting from like this A1 to AN. You design an input graph for the maximum independent set problem, right? And we rely on that graph, new graph, and we ask, hey, maximum independent set, solve this for me, tell me the answer, and I'll use it for my original problem. Okay, so I'm just going to go with the solution. So what I typically do when I do reduction is I try to study the key property of the two problems, right? The problem on the left, right? What we want is that, hey, each restaurant must be at least D apart. So everything that is less is not included. Okay. So how can independence set help, right? What's the key property? The key property of independent set is that two neighboring nodes are not included in the independent set. Okay. So if you look at it like, hey, the two problems seem quite similar. One wants to not include something. The other problem also doesn't want to include something. So we study these constraints and we make it similar. How? So if we think of the node, right, a node in the graph as a location, and the edge as the we give an edge if the pair of nodes have distance less than d. Okay, so if two pairs of nodes in the input graph to the independent set has an edge, we will exclude it in the independent set. Okay, so that means that if we give that pair of nodes with distance less than d an edge, right, that means they cannot be neighbors. Okay, if that's confusing, let's do the reduction. Okay, so node represents the location, right? Two nodes Vi and Vj have an edge if distance between the two locations are less than d. So let's say I focus on this 10 and 13. So this 10 and 13 is at least d apart, so I don't give them an edge, right? However, 11 and 12 is distance less than d apart, so I give them an edge in the graph. 11 and 12 is less than d, I give them an edge. 11 and 13 is less than d, I give them an edge. 10 and 12 is less than d, I give them an edge. Okay, so I give them an edge. 9 is far enough from 13, but it's close to everything else, right? 9 is at least d to 13, but it's close to like 11, close to 10, close to 12. Okay, so this graph, right, is the input to the maximum independent set problem. Okay, and then so this is the reduction. So the maximum independent set will tell you, oh, the best I can do for this graph is give you two nodes, which is the node 10 and 13 here, and they are part of the independent set, right? Because if you include anything else, they are going to be neighbors and with 10 and 13. So it will return the output 2, and 2 is exactly the number of restaurants that you can place here in the original problem. Okay, let's say the problem is from 9 to 13 only, okay, for the sake of graph. Okay, so this is like an example. This is an exercise for you to try out a reduction. Okay, the next question, right, will actually show in part BCD is to show that it can be solved greedily in polynomial time. And we have a reduction based on A, right? So the question we want to ask, right, because we have a reduction and it runs in polynomial time, right? Does that mean that, hey, we have a polynomial time algorithm for the McDonald's problem, Does that mean that we have a polynomial time algorithm for the maximum independent set problem? Okay, what we did is a reduction from McDonald to maximum independent set. Okay, we reduce. Why? Because we have an algorithm for McDonald's by making use of solve MIS. Something like that. So return answer, something like that, right? So this is a reduction from McDonald's to MIS. The question is, if we have polynomial algorithm for McDonald's, does that mean that we have polynomial time algorithm for the maximum independent set? Okay, so the answer is false, right? Because as I said, this is where it's important to know the relationship. Which one polynomial implies which one polynomial. So reduction in 4A was made from McDonald's to maximum independent set. And as I said, right, because polynomial time is in a sense like easy, right? It means that the problem is easy. So McDonald's is easy. Okay. If A is easy, it does not say anything about the maximum independent set problem, right? If A is easy, we don't know the status of maximum independent set. So just because the McDonald's problem have a polynomial time solution, and we also have a reduction from McDonald's to maximum independent set, it doesn't say anything about maximum independent set being easy or not. Easy? We don't know. Hard? We don't know. It doesn't say anything about. Okay, sorry. So if A is easy, right? It doesn't say anything whether B is easy or not. Okay, so let's just keep it at that. So that's why getting the direction of the reduction right is important. Okay, in a sense, we are relying on a more difficult problem. We rely on a problem that we don't know have a good solution to it. Okay, although we have a greedy solution for McDonald's. So again, this is the greedy solution. Victoria, this is the greedy solution that is in part BCD that we have in part BCD. And this problem is the MIS problem. Pictorially, that's what's happening here, right? We have a solution, a good solution that's done by greedy algorithm, not by relying on the maximum independent set, and it runs in polynomial time, but it doesn't say anything whether the MIS problem is easy or hard. Okay, so that's roughly it. I think I won't cover BCD. I think you can look at the slides for that. Okay. Again, apologies for taking more time than usual. I fully expected this, but I'm open for any further questions if you have now, in case that was confusing. I understand this tutorial might be confusing, so no shame in asking, really. Never a shame in asking. No problem. Yeah. Anything from you? Let me check. I guess not. Then I'll stop the recording. Okay. Okay, no problem. Yeah, see ya. Yep. So, okay. Okay. Thanks for watching. If you're watching from the recording.